Thank you for the introduction. Yes, I want to talk about 3D structured generative models. But before I do that, let me give a brief overview on the research problem that I'm really interested to solve. And to introduce that, I want to show you this image I just took this snapshot from a video of a person driving their car in the south of France. And when you see this image, I just want you to think about the kind of inferences you're making about the world that this image depicts. So we can make a lot of inferences about what are the different instances of objects in the scene. We have different peoples, different objects. We can make inferences on how far the objects are from us, so the depth, how far they are from each other. We can also make inferences about the things that are not directly visible in the image. So if you take this car, for instance, you don't really see what the front of the car looks like, but you can infer what that could look like, even though that information is not directly present here. The same if you like what lies when you turn your car along that street, what would happen? But we don't really know, but we have a good idea of like what are plausible solutions and what are definitely implausible solutions. We can look at the lighting and think about where the sun is. So just from this very small snapshot of the world, we create these rich models of the underlying world that allows us to perform our tasks and just move around in the scene and create intelligent decisions. The goal of my research is to build computational models that can do the same thing. I want to build models that can take information as impoverished, as little as a single image. And these methods should also be able to reason about the rich structures of the world that these images encode. Why is this problem challenging? Well, first of all, it's ill-posed. So just given this image, we do not have enough information to compute the structures of the world that this image depicts. So we have depth ambiguities, we have ambiguities between the lighting and the materials. And for the information that's not visible, like the front of the car or the scene that is that we're not directly observing, we have absolutely zero information. So we have to rely on priors. We can't literally just geometrically compute the solution of the problem. That's problem one. The second is uncertainty. Oftentimes we can reason about what the underlying world is, but we cannot reason very certainly. So again, if you think about what would happen if you turn your head to the left, you don't exactly know what's going to happen. We have guesses. We can think about what could happen. There's a street, there's the buildings, but we don't know exactly what they would look like. So we have reasoning about distributions, about uncertainty, but not point estimates. So our computational model should also support reasoning about uncertainty. And finally, supervision. Like how do we train these models? As humans, we do not look at data sets. We do not learn to see the world by looking at 3D scans. We learn by just moving around in our world, moving from place to place, interacting with objects, and just playing with the world. So similarly, these models should also be able to learn these rich representations just by watching and moving around. Here's an example of a recent project where we tried to create a method that fulfills these criteria. So here's a method that can take a single image, that's the image on the left, of a scene, and the goal is to do 3D reconstruction. It should compute the 3D scene that this image explains. And so the ill-posed problem is there because it's a single image. There's not enough information to compute the exact 3D. So it has to rely on learned priors. It has to reason about uncertainty because it does not know what exactly the depth should look like. But in particular, if we turn the camera around, what is the 3D scene that this particular image was part of, the larger 3D scene? And there we have a lot of uncertainty. And finally, this model is learned just by watching videos. So after this model is trained, you can take a single image and you can sample a distribution over 3D scenes rather than just get a single 3D scene because there is no one single 3D scene. And here you can turn the camera around and you can see what the different reconstructions look like. You can just move between the scenes. So you see that all of them are reasonably plausible, but there's not one which is possibly the correct solution. And you can do the same for objects. So if you take this image of a hydrant, and try to think about what this hydrant would look like from the back. I think in terms of geometry, for example, we would be pretty sure what it should look like, but in terms of texture and the structure of the paint, I don't think any of us would be able to exactly pinpoint which one is the right solution. And this model would be able to sample from the distribution over plausible estimates. So how do I go about solving this problem? The high-level idea is that we're interested in building generative models of the world. These generative models are not models over the observations, over the images and videos. They're models that capture the structured world. So just like any generative model, there's a prior distribution from which you sample. That's the latent space. There's a model that encodes the priors, and the outputs are the structured world models. So they encode the geometry, materials, lighting, all the structures that we're interested in inferring from our observations once we have trained our models. Once we have a generative model like this, we can train an inference algorithm. So now we know what the prior space over plausible 3D scenes are, over the plausible structures are. And now when we're given some very small amount of information, we can learn inference algorithms that figure out which parts of the latent space of this generative model explain this particular image. And this inference algorithm can be anything. It could be simple optimization, it could be search, it could be deep learning inference. But the point is that given an image now, instead of trying to geometrically compute the solution just based on the pixels, just based on the information of this image, we're searching in the latent space of the generative model, and that allows us to reason correctly and also reason about distributions. Here's an example of a structured generative model, a very popular one. These are 3D morphable models. So you have 3D models of the human face, and because there are 3D meshes, you have semantically well-defined parameters like the pose, the illumination, and the model has many more semantic parameters, but that gives us an idea of like what these structured models possibly look like. Let's contrast it with an example of a model that is not structured in my definition. So there's a model that is StyleGAN. It's a 2D generative model, really high quality, high resolution. It can sample very realistic faces, portrait images, but it does not capture the underlying structures of the world that explain these images. So we know how to generate an image, but we don't know what the underlying geometry, underlying lighting, the underlying scene properties were that led to the generation of these images. So not structured in this definition. The general idea of vision as an inverse generative process is really, really old, much older than even Blanson-Wether's paper on 3D morphable models in '99. But generally, the idea has kind of been that you pre-train the 3D generative model, typically on 3D scans. And once you have this, you do some inference, again, typically using some search or analysis by synthesis optimization process. And with that, you can get really good results for some specific instances, specific classes of problems. So for human faces, with Blanson-Wether showed that you can get like really nice results. You have to do a bit of manual initialization, but the results look pretty good. The problem, of course, is the first step. Like you need to pre-train the models on 3D scans. And that limits us from building general perception models. You can get 3D scans for some special objects of interest for human faces, for human bodies. But we're not going to scan every possible class of objects. We're not going to scan tigers and other animals and all the other interesting objects. And that's simply not scalable. And again, as I mentioned earlier, like as humans, we did not need to learn, we did not need to observe large amounts of 3D scans. So why should the algorithms need that? So the goal is that we skip that part. We're going to learn 3D generative models from 2D images, from 2D data, rather than 3D data. And that involves a bunch of things. So inference using analysis by synthesis is also kind of like slow, it's cumbersome, and it often does not allow us to train the generative models from 2D data. So in my research, I basically try to build inference methods and generative models that support scale, that support end-to-end learning that support training from large amounts of 2D data. As a general outline of what I want to talk about, I'll talk about self-supervised learning of the 3D morphological models that I just showed now of faces. Then I'll talk a bit about photorealism, about the quality of the scans we get, how we can use those for computer graphics applications, which require photorealism. And then finally, I'll talk about the idea that I just mentioned. It's like how when we start learning from 2D data, we can really enable scalability and learn models that extend to large scenes, where capturing them using 3D scanners is often completely infeasible. Let's start with the first thing, where we're going to learn the 3D morphological models of plants and weather, but from 2D data. What are these 3D morphological models in a bit more detail? They have these semantically well-defined and disentangled parameters. So you have the identity geometry space here, which just like every parameter controls how the geometry of the face deforms, moves from one identity to another. You have the reflectance space, controls the skin color. And then you have the expressions, like identity remains fixed, expression is changed. So very high level, semantically well-defined parameters. And then you have the scene parameters, it's like the pose and the illumination that I've shown you earlier. Before we get around to learning these models from 2D data, let me develop a framework that first integrates the inference and the generative models. So as I said, traditionally, the inference relies on search or optimization. In this paper, we showed that you can also do inference using a deep network, just using a simple encoder. A feed-forward pass of that encoder can give you the 3D parameters for any input image. So you take an image, the encoder gives us the parameters, and from the parameters, you can compute the 3D reconstruction because we have the pre-trained model with us so far. But how do we train these encoders? We do not have supervised training data. All we have is this generative model that is given to us and just a bunch of images. So we cannot really supervise in the 3D space. But we can do the same trick that the optimization methods and the inference methods, the traditional inference methods do. We can rely on differentiable renderers that gives us inductive biases. We can model the light transport that gives us, for every estimate of the 3D reconstruction, it gives us the synthetic rendering. And now we can say that the synthetic rendering should look like the input image. So we're essentially asking the encoder to amortize the search process and amortize the traditional analysis by synthesis process. This loss function will guide the network to give us 3D models that look like the input image itself, just like the self-supervised loop that integrates the inference and the generative models. The loss function is very simple. You render the mesh, you have the image, you just compare them in pixel space, and then you have the statistical regularizers from the 3D that just say that, oh, don't go too far in the variance space. And with that, you can get models. At that time, and I think even now, there are two kinds of main approaches that existed. The first one, which is the one from Richardson, which trains models supervised on synthetic data. So on real data, you don't have 3D supervision, but you can generate synthetic data that has supervision. But the synthetic data often lacks photorealism. It does not really model, there's a distribution shift. The distribution of synthetic images is far from the real distribution. And because of that, the results are not that great. What about the original methods that inspired us, the analysis by synthesis approaches? Well, it works much more robustly. So you can look at the last column here, which uses the same amount of information as what we use for training the networks. It's much more robust. It doesn't get stuck in local minima because it's using a lot of data and the amortized neural network inference. And it's also significantly faster. It's orders of magnitude faster. So that's great. And that means that we can train on large amounts of data, and we do not have to rely on this like minutes-long inference for every image. What are the limitations? Well, the output is restricted to the pre-trained 3D space. The 3D were built from 3D scans. And even though for faces there's a lot of interest, the number of scans is still limited, or at least it was limited to that model. And we cannot scan in the wild faces with beards, with makeup. There are a lot of issues with photometric reconstruction. So what ends up happening is that our models, if we get beards, you would often get these weird kind of results where the model would try to shrink and evade explaining these regions that it does not know how to model. And the same with synthetic models, like models trained on synthetic data. Like the synthetic data does not have these features, distribution shift becomes even wider. So ultimately, the 3D restricts us from generalization. And this is the original goal we started from. We said that the 3D models are kind of limit us, even for faces, but even more generally for the general problem when we try to model the 3D representations for just general phenomena, for general perception. So we want to learn from 2D data, but how do we do that? So because we have this integration of this inference and the 3D morphable models, like in this framework, we can say that, well, why do we have to keep the model fixed? We can now go ahead and update the models. We use backpropagation to learn the encoder. We might as well use backpropagation to learn the generative model. The problem with that is that if we learn it from monocular images, we end up in the same problems that we started with. Our initial goal was to take an image and learn to reconstruct plausible 3D models. And that required a prior. But if we say that the generative models themselves are going to be learned from monocular data, we're not going to be able to resolve the uncertainties, the ambiguities in these monocular images, which will limit us to find the priors in the first place. But there is a very easy way to fix this by using videos instead of images. And videos are also very commonly available. It's pretty much limitless amount of videos online. And if you see videos, you see the face of any person from different viewpoints in different conditions. And those constraints are enough, or might just be enough, to resolve the ambiguities that are present in monocular images, enabling us to learn the generative models as well. So if you look at just like this is just a data set of videos of like people giving interviews, and just like we can make simplistic assumptions that the reflectance of the face is consistent across the frames, and the geometry, you have two components again. You have the identity component, the person's identity, the geometry of that remains consistent, and you have a different expression for each frame. And with those constraints, you can create this simple method that takes multiple frames of a video. It has a network that consolidates these frames and gives us just like one estimate of the identity, shape, and appearance. It has these independent networks, these Siamese networks, that gives us estimates of the quantities that should be different for each frame. And then we have this learnable face model. In this particular case, we did not learn the expression model. We only learned the identity components of the model. But the identity components of the model are initialized from zeros, and you can learn that using the same learning framework as I previously introduced. You can render these reconstructions from the original frame's point of view and compare them. By the way, if there are any questions, just feel free to interrupt me. I'm happy with taking questions in the middle or at the end, whatever works best for you. Right. So with this, when we use videos, we can now start to learn the generative models by their own using simple backpropagation. And with that, you can get results like these. So you can take an input video, you can get 3D reconstruction that captures pretty much all the components that is required to render the full appearance of the face. And it can capture these faces in these challenging conditions, which typical 3D morphable models struggle with. Right. And this is even frame to frame. So the models work reasonably well that even without any temporal constraints, they are temporally coherent. And then in the previous case, the identity components of the model were learned and the expression was fixed. We worked on it more. And in this particular case, we also learned the expression model of the 3D from scratch. The only 3D information this model used was a single scan. So it's starting from one 3D scan and a data set of videos and images. It can learn to model all the 3D variations that were originally present in the 3D morphable models. Right. With that, I want to briefly talk about photorealism. And this might be a question that you're already thinking about. So we can do self-supervised reconstruction. We can reconstruct and render these 3D models that describe the videos that we captured, but we had to make several approximations to get there. So first of all, there's Lambertian surface. So we do not model any specularity, subsurface scattering, all of which is like really important for the appearance of faces, especially. The reconstructions are smooth. We didn't capture any details. We had this low dimensional priors that we applied on all the components of the model. We only model interface region, helps with topology. We were still using meshes. So these are all the approximations. And on top of it, when we were learning the models and videos, we assumed that the phase reflectance stays the same regardless of which expression you have, and that's also something that is not really true. So how can we bridge the gap that takes us from the quality of models that we can get when we're training from such in the wild data to what we need for computer graphics applications where we need photorealism and control? And a remark on this, on the approximations, I believe the approximations often are essential, they're critical. Without these approximations, these problems, the inverse problems, would not be tractable from the kinds of data that we're trying to use. If we had all the interreflectance and subsurface scattering, the amount of free variables that we would have, the constraints are not sufficient for us to discover the true values of those variables. And also in terms of speed and complexity, I believe that these approximations are critical to make these problems tractable. Okay, then how do we get to photorealism? Well, one way that I've explored is by using 2D generative models. 2D generative models, I've already shown you StyleGAN. The models are the same, the priors look exactly the same, but instead of modeling the explicit structures of the world, they directly model the observations in the images. Right. But the problem is that they don't have control. So you don't, there's no way, or we do not know how they could possibly capture the structures. But interestingly, if you think about it, if they can actually generate these images in all these different conditions, in all different poses and all different expressions, it's not very wild to think that the weights of the network internally capture these structures implicitly. We do not have a way to really extract this out of the network, but it's not crazy to think that they are somewhere in the activations and the weights of the network. And in recent work, we've shown that if you just like try to edit images just by the user providing constraints, that a point in the image should move to another point, and the only thing that the model is doing is to make sure that at every intermediate step the images are not going beyond the priors of the 2D model. So you just like say that this point should go there, and you just solve an optimization problem where you make sure that all intermediate images are not leaving the prior. You get results like these, which are really cool, and they kind of show that the priors they're reasonable, they're meaningful. The images smoothly change. The identity doesn't suddenly change out of in a very non-linear manner, which means that it is very likely that we can also extract the 3D structured variables from these priors. And one thing that I looked at earlier was to combine the properties of 3D morphable models and StyleGAN. So we know that StyleGAN has this amazing quality. 3D morphable models have this really nice control space. Can we build a mapping between the latent spaces of these models? So the idea is that we keep both of the models, the weights, pre-trained and fixed. All we are doing is trying to figure out how to go from the latent space of one model to the latent space of the other model. And once we do that, we can also embed a real image in the StyleGAN latent space. You can solve some optimization problem for that. And then you can also embed a real image into the StyleGAN latent space and try to control it using the parameters of the 3D morphable model. How does the mapping look like? So you have the StyleGAN latent code, and you have the 3D morphable model parameter. There's a simple network, just 2 layers, that takes these inputs and maps it to a new StyleGAN latent vector. And this new latent vector should correspond to the same identities, to the same image, with all the properties identical, except for the property that the 3D morphable model provides. So if I say that it should be this styling and latent code, but I give it a pose parameter here, that just means that the entire image should remain exactly the same except for the pose of this person, which should change according to the parameter that I've specified. And in this paper, we showed that this parametric model, this mapping, can be learned without using any supervised data. So all you can do is you can train this model. Everything is pre-trained and fixed. The mapping is trained such that you supervise the output to satisfy the constraints of the input 3D by doing 3D reconstruction techniques that I explained earlier. I'm not going to go into detail, but you can look up the details if you're curious, or just ask me more about it. But the high-level point is that you don't need any supervised data to train these mapping networks. You can train them self-supervised by keeping the models fixed. Once you do that, you can take real images, embed them in the styling and latent space, and you can get control like this. So you can just, like, it's just a user interface, it's fast, and you can just go and say that you want to edit the lighting, you want to edit the pose, you want to edit the expressions, and this gives you both photorealism and the intuitive control. So that's at least one way where these models, even though they do not really capture all the details, all the high frequency details that are necessary for photorealism, but they can still help in building actual tools that have the photorealism. The control space is still really valuable for guiding these 2D models. Right. With that, I want to get to the last part, which is how do we extend these models? So I've motivated the approach by saying that it's going to be general, and it's not going to be limited to faces. It's not going to be limited to any specific class of objects. So let's see how it can actually extend to large scenes. And this is a brief recap of the method structure that I had explained earlier. So we have the structured generative models, and we have the inference method. The structured models capture all the nice disentangled properties of the world, and the inference is the search algorithm, or the algorithm that maps the images to the latent space for this structured model. There are two kinds of inference methods that we looked at: analysis by synthesis and feed-forward neural net. So analysis by synthesis was the method that was used by the traditional 3D morphological models of Blanch and Bethe. Feed-forward, it was also used by the approach I just showed now, where we tried to embed a real image in the styling and latent space. That was also using analysis by synthesis optimization. And feed-forward neural networks is what I introduced for the first problem that I talked about, where you try to map an image to the 3D morphological model parameters. Well, if you do this, both of these approaches, so in the first case, in analysis by synthesis, you can also model uncertainty. The original papers of Blanch and Bethe and the follow-ups have shown that you can, instead of reconstructing just a single solution, you can reconstruct the distribution of solutions, often using Hamiltonian Monte Carlo, or by just initializing it from different state spaces. But it's slow, and as we've looked at earlier, it does not really support end-to-end learning that allowed us to train from 2D data instead of training from 3D data. Feed-forward neural network allowed us to train from 2D data. It integrated the inference and the generative models in a way that you could train everything jointly end-to-end. But these feed-forward neural networks, like if this inference was a neural network, that does not support uncertainty. It gives you a single estimate. It gives you a point estimate. And what does that point estimate look like if you're trying to model large scenes instead of faces? It looks like this. So the starting image is this. That's the input image to the method. And the output is the scene reconstruction. And if you just do a point estimate, it collapses to the mean estimate. And the mean estimate basically has very little information about the scene. It's definitely not plausible. You can have you can train the model for other behavior, like you can have it can seek the mode, but even then you'll get a single solution, won't capture the uncertainty in the distribution of spaces. So the inference methods that we have, both of them do not really satisfy the constraints that we have. The constraints are that it should be end-to-end learnable on 2D data, and it should be able to model and learn the uncertainties in the problem. So how can we learn end-to-end models that reason about uncertainty? And I want to introduce diffusion models, because that's, when I was thinking about the problem, the diffusion models were doing really well on image problems, on text-to-image problems, and it seemed like they definitely have the capability to model these kind of inferences. So diffusion models allow for probabilistic reasoning. Given a text input in stable diffusion or an image in, you can generate multiple plausible images that are all consistent with the text input. Probabilistic reasoning, yes. Scalable, yes, people have scaled it to large and large amounts of data, and they show that it works really well. It supports compositional scenes. It's large structures with like multiple objects. That's all great. That's the things we are looking for scalable models. How do diffusion models work? It's a generative model over images. The models I described were generative models over images like stable diffusion and Imagen. And the way these models work is that you sample from the distribution of random noise at test time, and this random noise is transformed to the distribution of plausible images. So the network learns the manifold of realistic images. And to train these networks, we are assuming that we have samples from the distribution we are trying to learn. So in the case of image generative models, we assume that the training distribution, the training data set consists of samples from the data set of images we're trying to model, right? So those are the X zeros, and these models are trained by adding noise explicitly to these samples from the training distribution. So you go from X0 to XT by adding the right amount of noise, and the network learns to denoise it just a bit. So it goes from XT to XT minus 1, where XT minus 1 has a bit less noise than XT. But there's a supervised problem, right? So you have samples from the training distribution directly, you add noise to it, so that becomes the input, which is XT, that's the input to the network, and the output is XT minus 1, and we can compute it, we have the supervision. And then at test time, we just run this iteratively. It starts from a complete noisy distribution, and iteratively over few steps, 100,000, whatever it was trained for, it learns to transform this noise distribution into distribution over the real manifold that it was trained to approximate. So this is great. It works very well for images, but can we use it for 3D inferences? Well, there's a problem. When we're trying to train 3D models that learn to sample distributions in 3D, we do not really have access to 3D data during training. So our assumption was we're going to learn to infer 3D, but we're only going to train on 2D data. We can train on images, we can train on videos. We do not have access to 3D scans. So in that case, we do not have samples of these X0 that we're trying to model. So how do we generate XT, and how do we supervise XT minus 1? We don't have the quantity that we want to add noise to in the first place. So this means we cannot rely on the naive way of training diffusion models. This is what our data looks like. Our data looks like we have some underlying signal. In the case of inverse graphics, the signals are the 3D scenes that we're trying to capture. But what we actually see are observations. So those are the images or videos. So let's say the parameter here, the phi, is the camera pose. So you can have a 3D scene that you have rendered from multiple viewpoints, and those are the different observations. So that's, let's say, a video, right? If I'm moving around in a house and I turn my head around, every time I turn my head around, that corresponds to a different forward model parameter, and I get a different image, but it all corresponds to the same scene. We only ever observe scenes. We only ever observe, observations, and we never directly see the scenes. At test time, our goal is that given one of these observations, like a single image, we want to sample from the distribution of scenes, which we never saw, right? So we developed this new framework for diffusion model that breaks this limitation of the original diffusion models, where you need to have samples from the distribution that you're actually trying to learn. In this case, we're trying to learn distribution over S, but what we do is we denoise the observations directly. So O context here is the observation that we're going to be provided at test time. So at test time, given this one observation, given this one image, we want to learn to sample from the distribution of signals S. Those are the 3D scenes. But what we do is that instead of denoising signals, we denoise the observations from a different viewpoint, from a different parameter of the forward model, right? If we do that naively without, with let's say the architectures of stable diffusion, you would still be able to do it given a single image. You would be able to learn the distribution over images that from another viewpoint. But you would still not be able to learn the distribution over the signals that led to the other viewpoint. So we solved that by introducing this new architecture where instead of directly learning to denoise this image from a different viewpoint, the network first takes these pairs, it computes an estimate of the 3D scene of the underlying signal, and then it uses the forward model, the renderer, to actually generate the denoised version of the target image, right? So the network is not allowed to do to be uninterpretable and just directly denoise it. The network has to first create an estimate of the 3D scene of the underlying signal, and only then it renders it to create the denoised version of the image. What would happen at test time? At test time, you would take this one image, the observation, the context observation, and you would set this to complete noise. You would set this to the random noise distribution. You would sample from the random noise distribution. And over time, when this t tends to 0, it would learn to sample distributions over clean images from different viewpoints, but also from the distribution of signals that describe the clean image from the other viewpoint. This was dense. Did it make sense? Are there any questions here?
Yeah. Hello. So do you have some illustrations here?
Yes, it's coming.
Yeah. Okay.
Let me show this here. This is a depiction, illustration of what's going on. So this is the image that you are given at test time, and you're trying to model the distribution over the underlying scenes. That's here. What you do is that you have a noisy version of the image from a different viewpoint, jointly with the clean image and the noisy image from a different viewpoint. You create an estimate of the 3D scene at time step t, the t corresponds to the noise level in the image from the target viewpoint. And then the network renders it. It's not a learned operation, it's a renderer that is physically based. It renders the clean estimate of the scene from the target viewpoint. And at test time, this is set to complete noise. You sample from the noise distribution. And over time, it learns to sample a 3D scene and sample the image from that viewpoint. And every time you sample a different noise distribution, you're going to get a different sample of the 3D scene. Did that help explain it better?
Yes. Okay. Thank you.
Cool. Right. So the framework here supports any kind of inverse problem where you have some structured signal and you only get to observe some observations, and you have a known forward model. In the special case of inverse graphics, this is how it really looks like when you can have a volume renderer, you can have a volumetric scene representation, and this is how you really sample at test time. Like an implementation level detail is that this model does not work really well as it is illustrated here right now, and that is because in this case this encoder does not get to see the noisy version of the image from the target viewpoint, right? So it processes these two images independently and only processes them together once it goes to 3D, once it lifts it to 3D. But the 2D encoders here don't actually see the information from the other viewpoint. And the way to fix it was to just add a deterministic conditioning. So in this case, there's no diffusion, it's a deterministic estimate. You just take the context image, you get the mean estimate of the scene, you render it from the target viewpoint, and that gets concatenated to the network from the target viewpoint. So the target, this encoder now gets to see both the estimate of the scene, the deterministic scene, so it gets to see the context image information as well as a noisy version of the target image, and that works well. That allows it to reason about the uncertainties and 3D structures. The baselines here are, first of all, just deterministic, the thing I showed you earlier. So if you just don't have any probabilistic modeling, you just do a deterministic modeling, you take an image, mean estimate, rendered, that's the output. There's another kind of baseline where you take the deterministic estimate, but you learn to denoise it, or you learn a diffusion model that condition on that deterministic estimate samples the distribution over images from that target viewpoint, but the encoder is just a 2D encoder. So the diffusion models architecture is just a 2D model. So this model also can give you good images from the target viewpoint, but it does not allow you to compute estimates of the 3D scene that describes these two images, right? Compared to the deterministic estimates, the results are as expected. So the deterministic estimate just collapses to this mean 3D reconstruction, which just like lacks any detail. Whereas if you do probabilistic reconstruction, you can sample from the distribution of the plausible scenes. This is comparison with the other baselines. So sparse fusion is a method that computes a deterministic scene, but then tries to fine tune it in image space. And in this case, that does not work at all in these challenging cases. There are more new versions of methods that follow a similar principle. I do not know how well they work, but in any case, any method that follows this image space refinement does not directly give you access to the distribution over the underlying 3D scenes. They only learn the distribution over the rendered images. Here are some more results. Let me just go through some of them. So in this case, on the top, you see this scene of a bedroom, and you can just take the camera with you and walk back, and it can generate you the door. I'm also showing you the depth maps. The depth maps obviously are not present in the training data set, but because the method learns the distribution of the 3D scenes, you can also render the depth, and you can compute the geometry. It's the same here, maybe. So you just see the bed, and you can just turn around, and it completes the rest of the room. There are a couple of longer sequences here. So in this case, you can go out from the current state of the scene, walk in a corridor right here, and then go to another scene, go to another room. And yeah, this is pretty much how the results look. This is a visualization of the variance in the results, just to show that if your viewpoint is close to the input image, there's not a lot of variance, which just makes sense because you have a lot of information that you can rely on. And as soon as you move away from the viewpoint, the more you move away, the variance in the renderings increase. This results on co-3D hydrants. And in this case, you can move around an object and get realistic reconstructions. Works well here as well. Right. So basically, this follows the same framework as I introduced earlier. There's an inference method. There's a generative model. They're trained end-to-end. They're trained on videos. They're trained on 2D data, and they can learn to model the distribution, the uncertainties, the 3D structures that arise when you just see a single image of a scene. I'm working on extending these models. So the goal is that we should be able to scale up these models in that they should be, we should be able to train them on unconstrained videos. We should just be able to stream YouTube and get models that can really reason about the structures, that can build these models of the world. So one limitation is that all the methods that the last method that I showed, in the case where you need videos, it needs to know the camera poses for each image in the video. And that's a big limitation in terms of compute, in terms of robustness. So we have ongoing work where we try to reason about the camera poses jointly with the structures of the scene that will allow us to not pre-compute these camera poses from these large data sets that we want to use. We want to reason about other kinds of interesting structures of the world. So for example, the objects, how can we figure out that the scene consists of multiple objects and where they are? So we have some work where we try to look at just a single image and try to reconstruct object-centric scene reconstruction where we have the 3D, but we also know where the objects are and which objects are where. We want to reason about dynamics. So if you have just a video like this where there's some motion in the scene, what can we really infer about the states of the scene that lead to this motion? So we can infer these physical properties that allow us to interact with the scene and apply forces after we've done the reconstruction for these interactive applications. And we want to reason about materials. We don't want to just reason about the geometry, but also about what is the material and what is the lighting in the scene. And the same kind of problems that we saw in the geometric reconstruction applies to these problems as well, where you have uncertainty, where you have ill-posedness, and where you have the lack of data. All of these are kind of preliminary, but the goal is that we're going to build models that have the right inductive biases, and they're general enough that we should be able to learn interesting structures and be able to train them on large amounts of data, such that we can get to scalable and general perception models. So this is the conclusion. We can learn disentangled 3D models from 2D data. That's the goal of what I'm doing here. There are still a lot of open challenges in inferring structured models and how we can use them in downstream applications. And there are like many open challenges, particularly like in terms of like how much of the world we should really model. This is something that I think about a lot. Like in terms of the inductive biases, should we model multi-bound slide effects that will allow us to get better materials and lighting? What about physics-based simulation for getting physical properties? How do we model objects, paths? To what extent should we explicitly add inductive biases versus let the models discover these structures on their own? That's the open problem that I think is very interesting. But with that, I'll end my talk. Thank you.